and we did mass of center of mass and moment of inertia. So now we are ready to start doing kinetics. So in this class, we'll essentially draw free body diagrams, write equations of motion, and do kinematics for rigid bodies. Okay, so these things can not only translate, but they can also rotate. Okay, so consider a rigid body, and the rigid body has, as we talked last class, has a center of mass. This is where you can think that the whole mass is concentrated. It's acted upon by external forces. Okay, so once we draw the free body diagram, then we get to write the equations of motion. And for a particle, we saw that there are just two equations. One is for equilibrium in the x direction. But for a rigid body, we have three equations. So first one is equilibrium in the x direction. The second one is equilibrium in the y direction. And the third one corresponds to rotary motion. So this is the external moments about the center of mass g equals I times alpha. Okay, and this will become clear when you do problems. Well, how do you exactly compute mg? You basically find the force and the distance from the center of mass and just take the cross product. So this is, if you like, this is r crossed with f, all the f external. Okay, so these fx, fy are x and y components of f external, and f external is nothing but f1, f2, f3.
Is it V cross F?
It's r cross f. Okay, so in this part we'll consider two special cases. One is rectilinear motion and the other is curvilinear motion. And really the way they differ is the coordinate of preference for rectilinear motion is going to be the Cartesian coordinates x, y, z, but for curvilinear motion we will use the tangential normal coordinates. That's usually the best coordinate to use. So two special cases. Rectilinear translation . Okay, in this case, so if the rigid body is just translating and it's not rotating, then the angular acceleration is 0, right? So the equations are as simple as fx equals ma x and fy is ma y, and then the moment mg is equal to 0 as alpha is 0, or this is only translation. Other case is when we do curvilinear translation. Okay, in this case, as I said, the coordinate of choice is the tangential and normal coordinates. So ft is mass times acceleration t direction, fn is mass times acceleration in normal direction, and because it's only translating, the net moment about g is 0 as alpha is 0, only translation. Okay, and well, what is AT? AT is alpha r, that's going to be 0, and then an is omega square r. This is not right, sorry. This is the rate of change of velocity in the tangential direction, that is not equal to alpha. Okay. So is this clear? So this is the special case when things are not rotating, which means that in effect they are like particles, effectively like particles, because the net moment is going to be, well, it's not good, it doesn't have rotary motion, but there's a caveat here. You would be using this formula to find the forces, okay, as you'll see in the problems. So you just cannot ignore that formula. We will use mg equals 0. So the recipe for analysis is essentially the same as chapter 13. First, you got to identify if it's a kinetics problem and if it is rigid body motion. Once you do that, then draw the free body diagram, write equations of motion, and then solve for the kinematics. So the third step is optional. So only if you have to find the velocity or the distance moved based on the acceleration. Okay, so let's start solving problems. Okay, so the jet aircraft has a total mass of 22 mg and a center of mass at g. That's given, it's right here. The location of the center of mass is also given with respect to the tires of the plane. That's going to be useful. Initially at takeoff, the engine provides a thrust of 2t equals 4 kilonewton, that's right here, and then t prime of 1.5 kilonewton. Determine the acceleration of the plane and the normal reactions on the nose wheel and each of the two wing wheels located at B. So we're going to find the forces at, so normal force at A, normal force at B, acceleration of the plane, and we got to neglect the mass of the wheels, and due to low velocity, neglect any lift caused by the wings. Okay, so the forces are as they are here. We got to find the normal forces on the tires and the acceleration of the plane. Okay, so since we are asked to find forces, okay, this is a kinetics problem. We need to invoke F equals ma. The reason why it's a rigid body problem and not a particle problem is because the plane has got distinct points at which the force acts. Well, for a particle, we don't really care where the force acts, because for a particle, we consider the thing to be a point mass. Okay, so this is a chapter 17 problem and requires us to invoke the three formulas, if needed. So equations of motion. Okay, another thing, which is what is the frame to use? In this case, the plane is going to only move in either in the x and y direction, right? So it's the best choice is Cartesian coordinates. This is really rectilinear translation. So with that, I'm going to draw the plane as a block. I don't care about the shape. I just want to ensure that the forces are at the right place. So there is a normal force at A, a normal force at B, and there is gravitational force. Okay, so for this case, as you see, it's very important where you apply the force. For a particle, you can apply it anywhere, but you just cannot put NA at a random place, because that will show up in the third equation, the summation of moments about the center of mass G. So then there is T prime, and then there is 2T. Okay. Are there any other forces? Are there frictional forces? So nothing has been told about friction, so we just ignore it. Okay, so that looks like I got all the forces on the. You guys should correct me. This is a free body diagram. FBD. Okay, so the three equations are sum of force in the x, sum of force in the y, and net moment about g. So sum of forces in the x direction. Okay, I would like to define the x-axis this way, y-axis that way, because in this problem they have not given me the x and y-axis. Okay, so the net force T is T prime in the x direction, plus there's 2T in the x direction. It's pointing in the positive x direction, equals mass of the plane times the acceleration in the x direction. Okay. So I do know what T prime is. T prime is 1.5, and 2T is 4 kilonewtons. So 1.5 into 10 raised to 3 for converting kilonewtons to newtons, and then 2T is 4 times 10 raised to 3 equals mass. So the mass is 22 mg, which is 22 times 10 raised to 3, that's the mass, times ax. Okay, so everything here except a is known. Yeah. So that's the thing. I just don't understand the notation of the book. I thought m is 10 raised to 6, but when it comes in this form, the book interprets that as 10 raised to 3. I will not give you such a thing in your exam. I will say it's 2,200 kilograms, so don't worry about it. I don't understand this notation. So solving for ax, we get 0.25 meters per second square. Okay, so that was easy. We still have to solve for NA and NB. So obviously we do equilibrium in the y direction. So the net force in the y direction, the external forces are NA acting in the positive y direction, NB also in the positive y direction, and mass times gravity acts in the negative y direction, so that's minus mg, equals mass times acceleration y in the y direction. Okay, So does the plane have acceleration in the y direction? It's not taken off yet, so the acceleration y is 0. This is 0 because it's still on the ground. So NA plus NB equals mass, which the book says is m is 22 times 10 raised to 3, the way it is in the way they've given it in the question, times 9.81. Okay, so I cannot solve NA and NB using that equation because it's one equation and two unknowns. If I want to solve for two unknowns, I better have two equations. So I need another equation, and this is where the third equation comes in play. The net moment about G is equal to 0. So I alpha is 0 because the plane is just translating, it's not rotating. Okay, so let's try to find the net torque or net moment about G. Okay, G is right this point. So the only force which acts along G is mass times gravity, and it will not have an effect on mg because only the forces which act at a distance from G will have an effect. Okay, so as t prime times the distance where it's the distance from where t prime acts to G. Okay, now there are two distances. There's the distance along the x-axis and the distance along the y-axis, right? The moment is only because of the moment arm in a direction perpendicular to the acting of the force. So in this case, the distance we are interested is in the y direction. We just have to find this distance. So that's going to be 2.5 minus, so the 2.5 is the distance from the ground, and 1.2 meters is the distance from the ground to G. So the net difference or the distance from G to the point of application of T prime is 2.5 minus 1.2, right? 1.3. So 1.3. Okay. The other thing we want to do is we want to look at the sign of the moment. Okay. So about point G, if you fix the plane at G, okay, and then if you apply the force, it's slightly above G, it will tend to rotate the plane in the clockwise direction, right? Because it's the action of the force is slightly above G. This is the plane. This is G. If I hold the plane at G and there's no forces, only I'm holding the plane at G, applying a force this way, it's above G, then this thing will turn in the clockwise direction. The convention we'll use is clockwise is negative, counterclockwise positive, so this is going to be negative. Okay, the next force is 2T. It acts at 2.3 from the ground. We need to find the effect of the 2T force about G, and so the distance between the point of application of 2T and G, the vertical distance, is 2.3 minus 1.2, or it's 0.9. Okay, so this is going to be 2T times 0.9. Again, this force acts above G, so it's going to produce a similar effect. It's going to turn the plane clockwise. Yeah, question? It's 2.3, yeah, right. 1.1. Okay, so that takes care of those two forces. We still have two more forces, NB and NA. NB is acting vertically upwards, okay, and we want to find the perpendicular distance from G. So now the perpendicular distance is the distance, the x distance from G to B. That's 3. Okay, so it's NB times 3. Okay, so what's the direction of the, is it positive or negative? It's negative because, again, if you take the plane, if you hold it at G, and if NB acts this way, it's going to turn the plane in the clockwise direction. Well, clockwise for me, it's like this, clockwise. So this is going to be negative. And then there's NA, which acts here. The distance from NA to G is 6 meters. So NA times 6. Okay, and what's the sign? It's positive. That's because, again, if you hold the plane at G, and if you look at the effect of the force NA, it tends to move the plane in the counterclockwise direction. Right? This is counterclockwise. So this is positive. And the net force is 0. So now we have one and two are two equations in two unknowns. Why is that so? Because we know t prime, we know what 2t is, so we don't know what these two things, NA and NB, are unknowns. But since we have two equations, we can solve for NA and NB. So to complete the problem, just solve for NA and NB using 1 and 2. So after doing that, and you can check me on this, NA is 73.38 kilonewtons and NB is 142.44 kilonewtons. Okay, any questions on this? Okay, so to summarize, first, when you see a problem like this, you got to first think, is it a kinetics problem? Then think if it's a rigid body problem. It is, because the point of application, the force matters. Then you got to think, is it, what coordinate frame should I use? In this case, it's translating, so it's good. The coordinate of choice is a Cartesian coordinate. So once you have all those three things, then it's a matter of applying the recipe, draw free body diagram, write the equations of motion. In this case, we didn't have to do kinematics. But something to note is, it's very interesting. There are three things which are asked in this problem: NA, NB, and A. And we had three equations. So most of the time when you see problems of this sort, you will always see that there will be three things asked, because there are only three equations which come from Newton's laws. And you can easily set those three equations to solve for the three unknowns. In this case, those were the three unknowns: A, and NA, and NB. Okay, if you have anything more than that, then you'll have to, then some other information will be supplied. Like if there's a friction force, you'll be told another equation will come from the relation between friction and normal force. So that would be another equation, and that is not a law. It is an empirical law. It has been found to be true, but it's not always true. There are different models for friction. One of them is Coulomb model. That's the one which we'll use. Okay, any questions?
Quick question.
No question? Okay.
So,
yeah. Tell me. Yeah.
So we don't have to account for NB as two separate wheels?
Okay, so once you found NB, then you can say that the force is divided by half. But that's again an assumption. Okay, if you're in the plane, if it's equally distributed forces, then yeah, there'll be equal forces. Otherwise, no. So yeah. So if you want to find forces on, the question says forces on each of the wheels. So in that case, if you take NB and divide it by 2 to distribute the force. Again, that's an assumption based on the fact that we are assuming that people are, seated in such a way that the weight is equally distributed. But that's not always true. Okay, I wanted to show you an interesting video of a street performer in London. Okay, so it looks like he's defying gravity. Looks like the field there, which is just making him sit without having any support. Let's analyze this guy using a free body diagram. Okay, let's call it FBD of street. Okay, so let's just consider one position when let's say he was sitting. So he was sitting apparently without any support, right? So he's clearly making ground contact here. So a free body diagram of this person would be, well, there is a normal force, right? There is gravity. Can be that there's no gravity there, right? There's no gravity in London. There's gravity in London. So there's gravity, and then we have to find the center of mass. Now, it's approximately true that center of mass per person is about over here. So the center of mass is right here. Okay? You agree with me? It's not close to his legs. Not here. It has to be there. Okay? Trust me, that's where it is.
We don't have correction.
What's that?
Correction.
As what?
Correction.
Friction. I think there's no friction. Well, we can put friction there, but I don't think there's friction plays a big role. No, I don't think friction plays a big role there. So that's mg. Okay, so that's all the forces. If you write the equations of motion, in the x direction, the net force in the x direction is 0, and this person is not moving in the x direction, so 0 is equal to 0. So that's true. In the y direction, mass times ay. So the net force in the y direction is mg acting down, normal force acting up, and then there is acceleration in the y direction, that's 0. So n equals mg. Okay? And there's a third equation because this is a rigid body, planar rigid body. mg equals I alpha. But, okay, mg is, this is g. So let's say that his thigh length is what? Let's call it, let's say this is d. Okay, so the net moment is only due to n times d, because that's the the horizontal distance. And if you fix him about g, and if you apply n this way, then this person is the moment is going to give you a counterclockwise motion. So this is going to be positive. Okay, and since this person is not rotating, this is 0. So this is saying that n is equal to 0, right? Because d is not equal to 0. But the first equation is saying n equals mg. There's a contradiction. They're missing something in the free body diagram. You know what we're missing in the free body diagram? There has to be another force here, more presumably a moment here. Or there might be, as I don't know your name, she said, there might be a force this way. There has to be that, because if there's no that force doesn't exist, okay, this force can be friction plus other things, okay. If this force exists, then what happens is this equation changes. It becomes n times d. This is, let's say, L. N times d is positive minus F times L, sorry, plus FL equal to 0, which means that F is negative ND divided by L, or minus MGD divided by L. So this F actually acts in the opposite direction. It acts in this direction. Okay, so now it's consistent. There's a N, there's a F. So this person has to have a force. It can be a force, or as I said, it can be a moment there. Let's say it's a force. So there should be a force there. So where his leg contacts the floor, there has to be some force coming which helps him to stay upright. So here's what he actually does. So this is the trick. Actually, this thing, that thing over there, helps him to apply the force. It should be pretty heavy, and it should, as he has a wide base, so it can apply a force. If it doesn't, if it's just a stick, then it cannot apply a force in the horizontal direction and cannot help him stand upright. And it's kind of interesting the way he's standing. He's using the maximum length of the orange of the support. If he was sitting the other way, in which he was trying to lean across this, he might have actually tipped over because the moment arm provided by the orange thing is not wide enough. So I'm out of time. There was one question I want to do, but I'll post it. I forgot to tell you that we are having got an email about the tutorial session. We'll have it from 10 to noon. Tomorrow, we start tomorrow in EV 3.04.30. That is third floor of the engineering building. It's the senior design room.
I just have a quick question. For this one, was it supposed to be all on my Mac?
Yeah, my bad.